Might be for decoration or for corrosion protection. You want to prevent it from corrosion. That is, you want to prevent the metal you are coating from reacting with water and air. I hope you know water and air are the main causes of corrosion. There must be presence of water before corrosion can take place. Then another reason for coating metals is durability. Durability. So later I will show you how electroplating is done. Then electro refining, for purification of metals. For purification of metals, electrolysis can be used for purification of metals such as copper, silver, gold, and zinc. Extraction, reactive metals. I think I've said this before. Okay, maybe not to you, but when you are extracting metals from their ores, there are different methods of extraction. You have electrolytic reduction, you have chemical reduction, and then you have thermal reduction, depending on the reactivity of the metal you want to extract from the ore. If you are extracting a very reactive metal among potassium, sodium, calcium, magnesium, aluminium, you have to use electrolysis. Don't forget, electrolysis is a method used for the extraction of very reactive metals like potassium, sodium, aluminium. Yes, potassium, sodium, calcium, aluminium, according to their arrangement in the reactivity series. But other metals that are moderately reactive, you use chemical reduction. Then metals that are least reactive metals like gold, metals like silver, you use thermal reduction, that is heat. You only
Excuse me,
use
sir.
heat. Okay,
Good evening, sir.
good evening.
Please,
You are
can
welcome.
you explain on the definition of electrolysis? Thank you, sir.
Okay, this is not our first class in electrolysis, right?
Yes.
Okay, so electrolysis is the chemical decomposition of an electrolyte. Electrolysis is the chemical decomposition of an electrolyte by passing direct current, or you can just say by passing electricity through the electrolyte. It's the chemical decomposition of an electrolyte by passing direct current through the electrolyte to liberate its ions at the respective electrodes. So once electrolysis takes place, ions are liberated at the electrodes. Substances are liberated at each electrode. It can be at the anode and at the cathode also, depending on uh, the electrolyte itself. Okay, the electrolyte itself determines which ion and the electrode used. We've done all of that, like factors that determine the discharge of ions at various electrodes, where I taught you guys the nature of the electrode, concentration of ions, and then position of ions in the electrochemical series. You still remember?
Yes, sir.
Good. Can I move on?
Yes, sir. Yes.
All right. So I was explaining electrolytic extraction of reactive metals, that electrolysis is used to extract highly reactive metals like sodium, potassium, calcium, aluminium, magnesium from their ores. Then in electrolysis, one, chlorine, hydrogen, sodium hydroxide, and oxygen are manufactured. Yes, if you remember the electrolysis of some electrolytes that we did in one of the previous classes, you discovered that some of the products at the anode and cathode can be chlorine, some will be hydrogen, some will be oxygen, some will be sodium hydroxide. So electrolysis can be used to produce these products, since some of these are the end products of electrolysis of some electrolytes. Anodizing and metal protection. That is formation of a protective oxide layer on aluminum surfaces. This one just has to, it concerns only aluminum. That is anodizing and metal protection. That is why aluminum sheets, for instance, like aluminum roofing sheets, last longer than the the former roofing sheets. That one is zinc. People don't use that a lot these days. That one reacts very well. That is why you discover that at a point it turns brown. It turns brown. But now many people use aluminum sheets, which will last for a long time because aluminum has the ability of anodizing itself when it's in contact with air or moisture, which is actually moisture is usually the cause of corrosion of metals. But corrosion doesn't usually affect aluminum because when aluminum comes in contact with moist air, it forms aluminum oxide. This aluminum oxide now becomes a protective layer for the aluminum sheet. That's why an aluminum roofing sheet will last very long. It's durable. Okay, let's move on now. So I've introduced electrochemical cells before. This is it. Electrochemical cells are cells. I told you that other names are galvanic or voltaic cells. Are cells that convert chemical energy into electrical energy or vice versa. So you now have, I told you we have primary, we have secondary. So in this case now, the galvanic cells include Daniel cell, and we also have what is called Leclanché cell. Okay, let me write it for you to see. We have Daniel cell and we have Leclanché cell. Those are the two categories of primary cells. I've explained what primary cells are to you, that they are cells whose chemical substances or chemical composition, when used up, cannot be recharged, but the cell must be replaced completely. Okay, there's nothing you can do about what the chemical energy has completely to replace the cell. For example, your Tiger Head battery, your remote battery, once the power is gone, there's nothing you can do than to throw it away and new one. But secondary cells are rechargeable. I'm telling you the main difference between primary and secondary cells. Secondary cells are rechargeable, so they can be used for a long time. Once it's low, you recharge and you use again. For example, car battery, your phone battery is a secondary cell. That's why you can use it for a long time. Once the battery is low, you charge and you use it again. You charge and you use it again. So such cells are called secondary cells. But primary cells cannot be recharged. You will see warnings. If you have read instructions in Tiger Head battery or all those types of battery, you will see warning in them that you should not even try to short circuit the battery. Don't even try to recharge them. It will just explode. It will explode. Okay, they are not meant to be recharged. All right. I'm just repeating what I've said before now for the sake of those that were not here when we just started. Please keep that in mind. We have primary cells, we have secondary cells. Primary cells are not rechargeable, secondary cells are rechargeable. So an example of primary cell is Daniel cell, Leclanché cell, which I've just given you categories as your Tiger Head battery, all those radio batteries, the remote batteries. Okay. Now, secondary cells, an example of secondary cell, I've mentioned them like the lead acid accumulator, which is car battery. Lead acid accumulator is the one that is used in cars, okay, to power motor vehicles. Then you have, let me use your phone battery as another example so that you can understand it easily. So those are examples of secondary cells. Those are examples of secondary cells. All right. So electrolytic cells convert electrical energy to chemical energy. See the difference between galvanic cell and electrolytic cells. Galvanic cells convert chemical energy to electrical energy. Galvanic cells convert chemical energy to electrical energy, while electrolytic cells convert electrical energy to chemical energy. Keep that in mind. I've just shown you some important things there. So, Daniel cell now. Let's see the composition of Daniel cell. Daniel cell has, you know that a cell must have must have electrodes, two electrodes, must have an anode and a cathode. Please don't forget that. There must be an anode and a cathode in any electrochemical cell. So the anode is the positive electrode, while the cathode is the negative electrode. Please don't forget that. The anode is the positive electrode, while the cathode is the negative electrode. The anode, oxidation takes place at the anode, while reduction takes place at the cathode. You know, by oxidation, I mean loss of electrons. You know, that's another definition for oxidation, loss of electrons. Reduction, gain of electrons. Reduction takes place at the cathode. Oxidation takes place at the anode. Don't forget that. Now, so Daniel cell consists of a zinc electrode in zinc sulfate. You know, when you are setting up a cell, let me even explain that. When you are setting up a cell, you have what is called electrode potential, which we will soon look at. You immerse an electrode into a solution of its electrolyte. For example, for my anode, you know, you are having two electrodes connected together now in the cell. Don't forget, a cell must have two electrodes. Okay, we call them two half cell reactions. Two half cell. Two half cell will give you a cell. So if I want to my anode side now, if I want to set up the anode half cell, what I'll do is that I will immerse the anode in the solution of the electrolyte of that anode. For example, let's say if copper is my anode, for instance, I will immerse a copper rod into a solution of copper electrolyte. For example, let's say copper sulfate. Copper sulfate is a copper substance and it's an electrolyte. It's a copper salt. You know, salts are usually electrolyte. So I will immerse a copper rod into copper sulfate solution. So in that solution, I will have copper ions in that solution because according to ionic theory, electrolytes dissolve in water into their various ions. Okay, electrolytes dissolve. When they are dissolved in water, they decompose into their various ions. They ionize. That is what ionic theory says. So once I have a copper sulfate solution already, and I immerse a copper rod into that copper sulfate solution. So what I've just done is I've set up an electrode potential of copper. Okay, I've set up an electrode potential of copper. Then I'll go to the other electrode and do the same thing at the other electrode with another substance, let's say zinc. So I will immerse zinc into a solution of zinc electrolyte. So I will now set up two half cells now. Once I have two half cells, what I've just done is that I have created a cell. I've created a cell. So let's see Daniel cell now. Daniel cell consists of a zinc electrode in zinc sulfate solution. You see that now. Daniel cell consists of a zinc electrode in zinc sulfate solution. That is half of the cell now. Then the other half, and a copper electrode in copper sulfate solution. You see that that is the other half of the cell. So you now have two half cells joined by a salt bridge. Joined by a salt bridge. Okay, salt bridge enables the migration of ions. Okay, it enables the migration of ions or electrons from one half cell to the other half cell. You know, that's how electricity is now generated. All right. So you have two half cells now in Daniel cell, zinc in zinc sulfate solution and copper in copper sulfate solution, joined by a salt bridge. Okay. So reactions now, remember that I told you oxidation takes place at the anode, Reduction takes place at the cathode. Please never forget that. So zinc now is the one that is being oxidized. And when you say a substance is oxidized, you are saying it's losing electrons. It's losing electrons. That's what you are seeing there. Neutral zinc. Zinc, if it's a neutral atom, is just Zn. But if it's losing electrons, it becomes Zn2 plus, which means zinc has lost 2 electrons. That's at the anode. That's what will happen at the anode. Zinc will lose electrons. Then at the cathode, copper will gain those electrons that zinc has just lost. Do you see that? There is movement of electrons now. There's movement of electrons. Zinc loses 2 electrons. Copper receives or gains the 2 electron. And you know, when there is gain of electrons, I've just told you, it is called reduction. So copper will be reduced, while zinc will be oxidized. So if you remember reduction and oxidation, they take place simultaneously in any reaction where any of them, either reduction or oxidation is taking place, the other must take place. Oxidation does not take place alone. It must be followed by reduction. Reduction cannot take place alone. It must be followed by oxidation. That is why, in school, you have done that topic. You did them together. Like you did reduction and oxidation at the same time. You must always do them together because you can't separate them. So zinc lost 2 electrons, copper gained the 2 electrons. Please don't forget, what I want you to be noting is, okay, which one was oxidized in this cell now? Which one was oxidized and which one became reduced? Zinc was oxidized, copper was reduced. So you can have questions like in Daniel's cell, in which electrode does oxidation take place? Or in which electrode does reduction take place? Or which substance is oxidized in Daniel's cell? Which substance is oxidized, which substance is reduced? You can see zinc is oxidized, then copper is reduced. So the overall reaction is this. You just combine the, the reactions together on both sides of the equation. Zinc and copper ion, then zinc ion and copper. You see the two half cells that you have. That anode, that oxidation is a half cell. Reduction is another half cell. So if you combine the left-hand side together, you have only zinc and copper 2 plus. If you combine the right-hand side together, you have zinc 2 plus and copper. You know the 2 electrons, they will eliminate themselves because they are equal now. So you don't need to include the electrons again. So you have zinc 2 plus. Please, this overall reaction, look at how it is written. You can be asked to write like what's the correct overall cell reaction in Daniel's cell. Okay, you have to know that, okay, zinc is the one that is oxidized, copper is the one that is reduced. How do you write it? This is how it is. If you don't know how to write it like this, you won't be able to get the overall reaction. So the left hand side, you bring them together. The right hand side, you bring them together. So you now have a complete cell reaction. So the Daniel cell notation is zinc immersed in zinc solution, and you have a connected to copper solution in which copper is also immersed. Okay, these double strokes, these double lines we are seeing here represent a salt bridge. Okay, these double lines represent salt bridge. It means you are having a half cell of zinc in zinc solution connected to these double lines. That is the salt bridge connecting this half cell to the other half cell of copper. All right, please, are we still together?
Yes, sir.
Okay. What's the direction of the flow of electrons now? Electrons flow from zinc to copper. That is from the anode to the cathode. Let me say it again. Electrons flow from the anode to the cathode. Don't forget that. Electrons flow from the anode to the cathode. So the one that is being oxidized is the one that will generate the electron. Right? You know, it is zinc, the anode that is oxidized, the one losing the electron. So that is where the flow of electron will begin from. Okay, it begins from the anode. Don't forget. So electrons flow from the anode to the cathode, producing electric current. Are you following me? Hope you are following me, please.
Yes, sir.
All right. Well, my other guys are not answering me. Shakiruddin, Emmanuel. Then who else is there apart from Vera? Precious, are you there? Where are they? Have they slept off?
Yes, sir.
Okay, okay. Some of them are waking up now. Please follow me, please. You have to. All right, let's move. I said we will look at electrode potentials. This some of the things I'll be saying, electrode potentials and half cell. So the next time you see half cell, half cell, half cell, okay, that's all they are talking about. They are just saying the anodic reaction and the cathodic reaction in an electrochemical cell. That's all. Okay, that is the meaning of half cell reactions. An electrode potential measures the tendency of an electrode to lose or gain electrons. That's an electrode potential. It measures the tendency of an electrode to lose or gain electrons. And you set it up by, explain that by immersing that electrode in a solution of its ions. By immersing that electrode in a solution of its ions. All right, standard electrode potential is this one is a kind of comparative analysis. You compare the an electrode with the standard, an arbitrary standard, which is hydrogen in this case. Okay, it's CBT that will be writing. Let me not give you too much details there. If it is SSC in our hand, there is a way to explain that very well for theory's sake. So when you see standard electrode potential, just know that they have done a kind of comparison with that metal against hydrogen. Okay, let me not go far for in that. So standard electrode potential is measured at room temperature. Room temperature is 25 degrees Celsius, 1 atmosphere, and 1 molar concentration. Okay, don't forget. Standard electrode potential is measured at room temperature 25 degrees Celsius, 1 atmosphere, and 1 molar concentration using a standard hydrogen electrode. Okay, the simplest way I can explain it is this. If I want to know the standard electrode potential of copper, for instance, let's say as a scientist, I want to evaluate the standard electrode potential of copper. What I will do is that I will set up a hydrogen electrode potential, then I will now set up copper electrode potential. Okay, hydrogen electrode potential is usually 0 0 at room temperature. Hydrogen is that's why they normally use it as the standard. Okay, for all the other electrodes will be 0 0. Okay, 0 0. It does not conduct any electricity. It has zero voltage. So whatever value I now have using my voltmeter, after setting up these two electrodes now, I want to get the standard electrode potential of copper. But I have to make sure these conditions are met. And what are the conditions? Room temperature, 25 degrees Celsius, 1 atmosphere, that's a standard pressure, and 1 molar concentration. Once these conditions are met, then I can set up my copper electrode against hydrogen electrode. Whatever my voltmeter reads, you connect these two electrodes to your voltmeter and it will read whatever value it reads. That is the standard electrode potential of copper, as the example I've just used. So this is still okay. This is still Daniel cell. Please, whenever you see this cell notation, okay, this zinc two plus double slash copper two plus, just know it's Daniel cell that you are looking at. It's very common in questions. Please, just know it's Daniel cell that you are looking at. So whenever you have a cell like that, how do you identify which one is anode? Let's say you are given this notation. How do you know which one is even the anode and which one is the cathode? It's very simple. Okay, it's very simple. There are two ways. In fact, there are even up to three ways of identifying which one is cathode and which one is anode. But let me just show you the simplest. The half cell at the left, okay, once a cell notation is written like this, the half cell at the left hand side of the salt bridge, okay, the one at the left hand side in this notation now is zinc slash zinc 2 plus, that is the left hand. That half cell is the anode. Then the one by your right after the salt bridge is the cathode. Don't forget that, because you might have a cell notation and you have to identify the anode or the cathode, or you can be given a cell notation and then they give you certain electrode potentials and ask you to calculate the electromotive force of that cell. Okay, if you don't know which one is anode and you don't know which one is cathode, you can't calculate electromotive force, because in the formula you have to use the anode and the cathode, the electrode potentials of the anode and the cathode. So if you don't know which one is anode and you don't know which one is cathode, you are lost already. So don't forget, the one by the left is your anode, then the one by the right of the salt bridge is the cathode. Another way is to look, okay, if you understand this one now, let me know, trouble you. Let me not trouble you. Hope, do you understand what I've just said? Hello? Hello, are we
Yes, sir.
still together? Okay,
Yes, sir.
all right, all right. You understand what I've just said very well. So if I write a cell notation for you now, you can identify which one is anode and which one is cathode, right?
Yes, sir.
Okay. So in this case now, I can also write a cell notation like this now. Let's say you have a cell notation like this, and I just ask you, which one has been oxidized? If you know the anode, you know which one has been oxidized. If you know the cathode, you know which one has been reduced. Okay, that's why I'm making all this noise, because they are all connected. Anode is connected to oxidation, is connected to loss of electron, and is connected to EMF as a formula. Cathode is connected to reduction, is connected to gain of electrons, and is also in the EMF formula, electromotive force. Okay, electromotive force is the potential difference of a cell when it's not connected, like it's not in use. Okay, electromotive force is the potential difference of a cell when it is not in use. Like when you remove battery, let's say a remote battery, you remove, before you put that battery into the remote, the power, the potential difference of that battery is what is called electromotive force. Okay, it's what is called electromotive force. If you check, for example, Tiger Hair battery, you see that they write 1.5 V, 1 plus 1.5 volts in the battery. Okay, now it means the potential, the electromotive force of that battery before it is in use, the electromotive force is 1.5 volts. So as you begin to use it, it begins to deplete and deplete until there is nothing left of the battery. All right, so let's see half cell reactions. Now let's say you are given half cell reactions like this. You can be given stuffs like this and you asked to calculate the EMF. Okay, it's what I want to teach you now. It's very important. Okay, that's the only calculation in electrochemical cells, half cell reactions. Now you can have half cell reactions like this with their electrode potentials. That E naught you are looking at is the electrode potential. For example, in these half cell reactions now, the electrode potential of zinc is minus 0.76 volts. The electrode potential of copper is 0.34 volts. So if I'm asked to calculate the EMF, so a person can now say I should calculate the EMF or I should calculate the cell potential. Please don't forget, they are still saying the same thing. They can say you should calculate the cell potential or the EMF of the cell, electromotive force. Anyone you see is still the same. They're asking you the same question. No need to be confused. They can ask you to calculate the cell potential or the EMF of the cell. So you use the formula standard electrode potential of the cathode minus standard electrode potential of the anode. Very simple. Standard electrode potential of the cathode minus standard electrode potential of the anode. So you see why I was saying that you must be able to identify your anode and your cathode in a cell reaction, like in a cell notation. You must know which one is the cathode, you must know which one is the anode. Else you can't know the EMF of that cell. So since zinc is in the cathode, I'm just using Daniel cell as an example. Any cell can be used. Okay, it doesn't always have to be zinc and copper. So zinc is the cathode now. So zinc is the anode and copper is the cathode. So I will bring their electrode potentials into the formula. Now the electrode potential for the cathode is plus 0.34 volts. Then minus the electrode potential of the anode. The electrode potential of the anode is minus 0.74 volts. You know, zinc is the anode, copper is the cathode. Zinc is the anode, copper is the cathode. Don't forget. So you use the electrode potentials in that manner also. If you do the calculation, you have plus 1.10 volts. Plus 1.10 volts. When the EMF, when you calculate the EMF of a cell, when you calculate the cell potential, and you are having a positive value, so we normally say it is spontaneous, it is spontaneous, all right, that it is feasible, such reaction is feasible, it is spontaneous. But if you are having a negative EMF, it is non-spontaneous. You are predicting, you can be asked to predict whether a cell reaction is spontaneous or non-spontaneous. How do you determine the spontaneity of a cell
Excuse me,
reaction?
sir.
Okay,
Please, can you come back on the formula?
okay, formula is electrode potential of the cathode minus electrode potential of the anode. You are seeing it there, right? You are seeing the screen, right?
Okay, yes, yes.
Uh-huh. So, and the cathode, the one that is gaining electron is copper, and the electrode potential of copper is 0.34 volts. The anode is zinc, is one that is losing electron. The electrode potential is minus 0.76 volts. So if you bring those electrode potentials into the formula, you are going to have plus 1.10 volts. Is that okay?
Yes, sir.
Uh-huh. Now, I was saying that this value, the value of EMF, determines the spontaneity of a cell reaction. If the value is positive, like this one, this plus 1.10 volts, if it is positive, it means that cell reaction is spontaneous. But if you have a negative value, it means it is non-spontaneous. Don't forget, it is non-spontaneous. Okay. Now, if you are given half cell reactions like this, where you can't tell which one, if you just look at these two half cell reactions now, you can't tell which one is cathode, except that you already know. I've already told you about Daniel cell. You already know this cell reaction is for Daniel cell now, and in Daniel cell, zinc is the anode, copper is the cathode. You quickly fix the values and you get your answer. But it's possible that you are given a cell that you are not familiar with with the composition of that cell. How do you identify which one is the anode and the cathode? The one that is, please listen to this, okay? The one that is more positive is the cathode. Let me say it again. The one that is more positive is the cathode. The one that is more positive, when you are giving cell reactions that a cell reaction that does not directly show you which one is anode and cathode, What you need to do is look at their electrode potentials of the half cell reactions, the two half cells. Then the one that is more positive is the cathode, while the one that is less positive is the anode. Don't forget, don't forget, don't forget. All right. Applications of electrolytic processes. I think I've said something about that just now at the beginning. That
Sorry,
was where
is
I
it that
started.
none of it is more is negative, like completely negative?
No, I said less positive. Less positive can mean negative
Negative.
too. Yeah,
Okay.
good.
All right.
So touch this one at the beginning. I'll touch this one at the beginning. So methods of protecting metals from corrosion. Okay, how do you protect metals of corrosion from corrosion? Okay, the syllabus wants you to know these methods. Various methods used to protect metals. One, painting and greasing. Electroplating, which I said I will explain now. Yes, because there's a reason. Once I do that now, you know why I've been very particular about electroplating. Alloying, combining with metals. Of course, we all know alloys: bronze, brass, alnico, soldering, solders. Okay, let me just say solder, or we normally call it soldering iron for those who are very interested in fixing electronics. They normally call it soldering iron. That thing that they normally use to solder wires is an alloy. Okay. Then galvanization, coating iron with zinc. Don't forget, coating iron with zinc is what is called galvanization. Then cathodic protection, connecting metal to a more reactive metal. Connecting a metal to a more reactive metal to prevent oxidation. So these are different methods of protecting metals from corrosion. These are the different methods of protecting metals from corrosion: painting and greasing, electroplating, alloying, galvanization, cathodic protection. You have to know what each one means. Okay, you have to know what each one means. So let me take you to electroplating that I've been mentioning. I've defined it here is the coating of a metal with another metal. For example, you can use any metal to coat it depending on the kind of properties you are looking for in the final product. If I want to coat zinc with silver, is electroplating. So what will happen is that the reason why you are electroplating is one, for durability. You want to increase the durability, you want to prevent the metal from corrosion, just things like that. Okay, so one of the you're having two metals now. Before electroplating can take place, you are having two metals in place. The one you want to coat and the metal you want to use to do the coating. Let's say you want to coat aluminium with silver. Okay, so aluminum is the metal you want to coat. Silver is the metal you are using for the coating. Okay, now one of them has to be the cathode and one has to be the anode. Okay, let me take you gradually. Please pay attention to that. Electroplating, this definition is the process of depositing a thin layer of one metal onto the surface of another metal using electrical energy. Of course, they will not ask you to define it. I just want you to understand it very well. It's an application of electrolysis, okay, that we have just seen. So how do we carry out this electroplating? So the metal you want to coat, okay, the object to be plated, you can still be using coating. The metal you want to coat must be your cathode. Don't forget. The metal that's the negative. you use that one as your negative electrode. Then the metal you are using for the coating, okay, must be your anode. Don't forget. So if I want to coat uh, steel, okay, let me know. Let's say I want to coat iron with aluminum, for instance. This is how alloys, some alloys, some of the things that we use, for example, all those stainless steel, things that last, that don't get corroded easily. This is how they are built. Now, if I want to coat iron with aluminum, so iron is going to be my cathode, my negative electrode. So I will fix the iron at the cathode, while I will fix the aluminum as my anode. So because it is the anode that is losing electrons, so there will be migration from the anode to the cathode. So part of the anode will uh, cover the surface of the cathode. That is the essence of electroplating. So at the end, what you're having is a kind of, for example, the example I've used now is iron being coated with aluminum. You will have iron inside a protective cover of aluminum. So the example I use in this particular slide you are looking at is, let's say I want to coat a steel spoon. I've seen questions like this in past questions, in UTM questions, okay? In the coating of steel spoon with silver, which one is the anode? You can see a question like this, or which is the cathode? And then they will start listing the options. They can say steel, the steel spoon. They can say the silver in the option. So you have to know which one is correct. I've just said what the object you want to coat is the cathode, while the object you are using for the coating is the anode. So here now, if I want to coat steel spoon with silver or with gold or all those things, to make it look flashy and all of that, I want to coat a steel spoon with silver. So that steel spoon is going to be my cathode, while the silver is going to be my anode.
Please, can
All
you come
right.
again?
If I want to coat a steel spoon with silver, okay, I want to cover it, I want to garnish, I want to furnish it so that when you look at it, you just think it's silver spoon you are buying. Now, the steel spoon is the cat we act as the cathode. I will set it up as my cathode. Then the silver that I want to use to coat it will be my anode. Do you understand?
Yes, sir.
All right. It's as simple as that. Don't forget. The object you are coating is the cathode. Then the object you are using for the coating is the anode. All right. So I have a few questions here now. Okay. So question one. Let's just answer this together before we move on. Before we move on, because I want us to touch another topic. We have the time. Number one, which of the following methods? Everybody, we are going to participate. Everyone is going to participate. Which of the following methods is purified or is extracted? Let me use extracted. Uh, okay, okay. We have not done methods and their extraction now. You may not know this number one, but if you know it, please answer this number one question. Which of the following methods is purified commercially by electrolysis? Who knows it? Are they there or they have forsaken me?
Option B.
Okay, next person. Which of the following metals is purified commercially by electrolysis?
Option A.
Option A. Are you sure you people are just you are trying to do you are trying to play that game that children used to play? Another person will call option C now. Yes, I'm waiting.
We are
Okay,
just,
that one. Yes, yes, I'm with you.
I said we are just two. It's just two of us.
Online right now.
Yes, sir.
Okay. Emmanuel has fled. And Precious, I don't know why Precious is not online today. Azim too is not online. Okay, so we'll do metals and metals. Once we do extraction of metals now, or we'll touch that one. Don't worry. We'll do alloys. We'll do a lot there. But the ones we've done so far under electrolysis, the ones I actually want to test you people on. So I will explain this number one. But okay, let me check this number two, whether it's still connected. These are actually ETM questions. How will a metal X, which reacts explosively with air and with dilute acid, be best extracted from its ore? Aha. Okay, it's still metals and their extraction. Wait. Let me see the one that resonates with you now. Aha, this one. In the electrolysis of brine, the anode is what? You know, brine is concentrated sodium chloride. I've taught you that. During the electrolysis of brine, concentrated sodium chloride, if you still remember your electrochemical series and how electrolysis takes place, how ions are discharged at each electrode. This case now, the electrolyte is concentrated sodium chloride. I was emphasizing on the effect of concentration on the discharge of ions. Now, what's the anode? That's the question. In the electrolysis of brine, the anode is what? Concentrated sodium chloride. Okay, let me explain this one. Please, I want you to listen very well. I told you in one of the previous classes under this electrolysis that you have what we call inert electrodes. Inert electrodes are electrodes that do not interfere with the reaction, with the electrolytic reaction. It does not interfere. It's as if it does not participate in the reaction. There are other electrodes that will affect the reaction. If you cause a problem, it will affect the discharge of ions. Now, the common example of an inert electrode is carbon electrode or graphite. Okay, when you see graphite, they are still talking about carbon. You know, graphite is an allotrope of carbon. So they can call it a carbon electrode or graphite. Please don't forget that. Then, if I platinum reacts very well with chlorine, so you can't use platinum in the extraction of anything that has chlorine. If you react with that chlorine, you can't use a mercury electrode. If you also react with chlorine, there are some electrodes like that that you can't use, especially if you are extracting anything that has chlorine in it. You can't use zinc, you can't use copper. The only thing you can use is graphite electrode, which is carbon. Don't forget that, because carbon is a completely inert electrode, completely inert. Number four, iron can be protected from corrosion by coating the surface with what? Iron can be protected from corrosion by coating the surface with what? Who knows the answer? We've just done application of electrolysis. Anybody? Zinc. Okay, you use zinc to coat the surface of an iron to prevent it from corrosion. Okay, you use zinc. Then here, which of the following ions requires the largest quantity of electricity for discharge at an electrode? Which of the following ions require the largest quantity of electricity? Yes. Is there anybody that can answer this question? For you to answer this question, you have to press your calculator. If you do not press your calculator, you won't be able to answer the question. You won't know which one is correct. And why will you press your calculator? Because you know that remember 1 Faraday is 96,500. Okay, you can even just use Faraday to know the answer here. But Faraday, there's a relationship between Faraday and moles of electron. I've taught you that one electron will require 1 Faraday to be deposited. 2 electrons will require 2 Faraday to be deposited. 3 electrons will require 3 Faraday. So in that sense, univalent metals require 1 Faraday to be deposited. Divalent metals require 2 Faraday. When I say divalent now, metals that have 2 plus, they are divalent. Then trivalent metals require 3 Farads to be deposited. So in your own estimation now, which one of them do you think will require the highest amount of electricity to be deposited? Are you still with me? Are you there? Don't worry, I will answer the question in case you are confused, but I want to know whether you are hearing what I'm saying.
Yes, sir.
Okay, so let me explain how you answer this kind of question. These are the kinds of questions you have in exams. Now, for you to know which one will require the largest quantity of electricity. Now, copper is divalent. So for you to deposit 1 mole of copper, you need 2 Farads. Now, 2 Farad, but you now have 2.5 moles of copper. 1 mole requires 2 Farads. Okay, now you're having 2.5 moles. That is 2.5 times 2. So somebody should be pressing the calculator so that we follow each other. So for you to deposit 2.5 moles of copper now, the quantity of electricity will be 2.5 moles times 2 Farad. What are you going to have?
Times what, sir? 2.5.
2.5 times 2 Farad. You know, copper is divalent. Copper is divalent, so it will require, normally it's supposed to have 2 Farads. But if you now have 2.5 moles of copper, you have to multiply the 2 Farads times 2.5.
The answer is 5.
5, good. That is for copper. Then let's go to option B. Chlorine is -1. That is it's univalent also. So which means it has, that is 1 Farad. 4 times 1 is 4, right?
4.
4 times 1 is 4. Then let's go to option C. Aluminium, 3 Farads. You know, aluminum is trivalent, 3 Farads. So 2 moles times 3, 2 times 3 will give you
Yes.
6. Then let's go to the last one. Sodium is univalent. 3 times 1, 1 Farad. 3 times 1 Farad will be 3. So which one requires the largest quantity of electricity?
Sodium.
Largest, are you sure? Which one has the highest value there from your calculation now? Which one has the highest value?
Option C.
Right, that is 6 Farad. Is that not so?
Yes, sir.
Yes. Yes.
Oh, yes, good, correct. That's the answer. Okay, 6 Farad. That is higher than the others. For copper, you have, that is 2.5 moles of copper. You need 5 Farads, but for aluminium, you need 6 Farads. Okay, that's that for electrolysis. Let's uh, let's move on to a new topic now. Let's move on to a new topic. I will send these slides to the Telegram group for your use. I probably have sent it before. Okay, I'll check. Then let's move on to something new today. This one does not require calculation. It's just to move you on in your syllabus for us to go
Sorry,
further.
excuse me, sir.
Yeah,
Please, can you send the notes in PDF or
in
Word?
PDF. Okay, okay,
Mm,
no problem.
thank you, sir.
All right. Why you can't open PowerPoint or what?
I have to go through, I have to make use of my computer then. So it will be easier for me to just, if I want to print it or write it.
Okay. All right,
Yes,
it's
sir.
fine. So we want to look at air. Our topic, the one I want to introduce to you is air. Okay, what the syllabus wants you to look at is composition of air, separation of the various components, constituents that are in air. No, air is a mixture. It contains many constituents. How do you separate them? Then uses of these constituents of air. That's all they want you to look at in air. So when you know what to look out for in an exam, there is no need for anxiety at all. Just do your preparation and go and kill the exam. All right, so we begin from what they want us to do. Why is air a mixture? Why do we say air is a mixture? That air is not a compound. Why is it a mixture? Number one, no chemical combination between the gases. You know, in air, you have
Excuse me,
H2O. Yes, yes.
but air has a particular definition. If there
Uh,
is, can you before we proceed to why air exists as a
okay.
mixture?
Air does not have definition.
Okay.
Because air is not just an entity on its own, like it's composed of many things. So if I want to define it now, I'll just end up saying that air is a substance, for instance, or is a substance that is composed of constituents like, then I'll start giving you the examples of the constituents. So no special definition, so to say. So air is a substance or a mixture containing water vapor, that is H2O in gaseous form now, H2O in the gaseous form, water vapor, noble gases, nitrogen, oxygen. Those are the constituents of air. So if I want to define it, I could just say air is a mixture whose constituents are this in certain percentages because each of them has its proportion in the mixture. That's all.
All
Do you
right, sir.
understand that? Mm.
Yes.
So now, air constituents of air, I've just listed them.
Excuse me, sir, I can't hear you again.
Hello, Vera. Shakurudin, is the class over?
No, ma.
No,
Maybe
ma,
it's
I think we have a connection problem.
Please, it's up to 5 minutes he left the class. Hello, Vera.
Hello, ma, what do you say?
Has it been long? Is there having the network issue?
Yes, ma.
I've sent a message on WhatsApp, but he hasn't seen it. I've called him. It's another call. So when I speak with him, I will get back to you guys. So has it been up to 10 minutes he left? Do you think it's been up to 10 minutes he left? Do you think it's up to 10 minutes that he got disconnected?
It's up to that, ma.
All right. So I think we should end the class. I'll speak with him. If there's anything else he needs to do to complete the lesson today, maybe he'll continue it in Telegram. So the class is supposed to end at 8. So there's no need waiting for him.
All right, ma.
Okay.
Mhm.